Okay, so let's do this, you guys. All right, so here's your sample problem. All right, so check it out. We got a 10-kilogram block sliding along a surface, which I'll get to in a second, at 8 meters a second.
She's not frictionless.
Not frictionless. We'll get there in a second. Yeah. All right, 10-kilogram block sliding along at 8 meters a second. It's going to slide 0.8 meters before it hits this spring. The spring has a spring constant of 5 newtons per meter. Okay? There is friction on the whole surface. The whole thing has friction before the spring and after the spring. Coefficient of friction is 0.6. My question is, how far will the spring compress before the block comes to rest? Okay? So take a minute and see if you can figure it out. There are a couple of ways of doing it. You can do it in one big step. You can do it in 2 small steps. All right, so again, the question is, well, eventually, it may or may not. I guess it depends on if the force of the spring is bigger than the friction. But we're just going up until it stops. And I want to know, how far does the spring get squished before it stops? So X stop equals question mark. How far does the spring get squashed before the block stops? All right, I'll give you a minute to work. All right. So in my mind, there are 3 points that we care about, right? There's point A when the block is first moving. There's point B when the block hits the spring, like when it first makes contact with the spring. And there's point C where it stops, right? All right, now, did you guys have did you guys think in terms of total energy, kinetic energy? How did you do it? Okay, yeah. So to me, my knee-jerk is to do it using kinetic energy. You can do it using total energy. It doesn't really matter. It boils down to be the same thing, basically. Okay? Oh, you know. All right, well, so here's, I guess, the problem, though. So suppose we call the distance that the spring squishes x. Cool. Then, as the block slides to rest, what distance does it move total? 0.8 plus x. So the distance over which friction does work is different than the distance over which the spring does work. Does that make sense? Because friction has that extra 0.8 meters to do work on it. All right? So my knee-jerk reaction is, let's figure out what the total energy or what the kinetic energy looks like at point B. And you don't have to do it that way, but that way works. All right? So from A to B, what do we know? Well, our change in kinetic energy is equal to the work done by friction, because that's our only force, right? Other than gravity and normal force. Good? Follow? So the kinetic energy at A, that's 1/2 times the mass times the velocity squared. Oops. So the kinetic energy at B minus the kinetic energy at A equals the work done by friction. Did you guys all find the force of friction?
58.8.
Just by doing normal force times coefficient, right?
Yeah.
Too hand wavy, or are we good with that? All right, so the work done by friction between points A and B is going to be negative 58.8 times 0.8, right? Because that's how far it goes between points A and B. Force times distance. Good? And in your head, you should be thinking, oh, that's right, friction's constant. So I can just do force times distance, right? Good? All right, and solve this. And what you find is that the kinetic energy at B turns out to be, I think it's 272.94. 96. Ah! All right, is everybody okay with that? Problems? 272.96. I want to make sure we got about 8 more minutes here. Well, probably 5, really, realistically, because my clock is slow. Okay, so are we good?
Yes.
All right. So now, let's make a note of that. So I know that the kinetic energy at B is 272.96 joules. What's the total energy at C going to be?
7.38.
Is it going to be too small?
What are we trying to find here, you guys? What's the question? How far the spring compresses when it stops. So what's the kinetic energy at C? 0. Yep, but it's going to be elastic. But we don't know what it is. Okay? So, here's what we know. We know the kinetic energy at B is 272.96. Kinetic energy at C is 0. I know that my network is my change in kinetic energy, right? So my change in kinetic energy is negative 272.96. That's got to equal the work done by what?
UPE and
Friction and the spring. EPE is the energy, not the force. I knew you knew what you meant, but just... Everybody good? All right, cool. Well, so that's negative 272.96 equals the work done by friction. Well, we're trying to find X, right? So in terms of X, what's the force of friction, or the work of friction? Negative 58.8 times X plus the work done by the spring. How much work is done by the spring? Negative 1/2 kx squared, right? So minus 1/2 times, what is k? 5x squared, right? And solve it.
Wait, how come it's negative?
Because as the question was, why is the work done by the spring negative? So reason 1, as the box moves to the right, which way is the spring pushing the box?
left.
To the left. Anytime your force opposes your displacement, that's negative work. Secondly, do you agree that the spring is going to decrease the kinetic energy?
Yes.
Right? So it's got to be negative because it's taking away that, it's helping friction take away the kinetic energy. Follow?
Yeah.
Thoughts?
Okay, so is the reason why 3 was so hard was because that step 2 where it's like the total energy when you did KU minus KUA, you also had to throw in like the change in
Yeah, there's a lot going on in that problem. I just need to get rid of that. All right, so if you solve this, you get 2 answers. You get an answer of, it's like negative 27.5 and 3.9 something or other. Which answer do I want? We want the positive one, and the reason that we want the positive one is because I need to ensure that the work done by friction ends up being negative, right? And if I put in negative 27, then I get negative 58 times negative 27 makes that positive.
For work, can't distance just not be like
It can be, but
and this is good stuff. Well,
so that would mean back here,
yeah.
you know? Does this make sense?
Yeah.
Okay, so to me, this feels reasonable.
Okay.
But now we're not going to get this.
Yeah, but now we're gonna get
Now this is not gonna be
We'll see.
That process seems manageable. All right? I'm going to post this video because at the very end of 4th hour, I goofed up these signs here, so I just need to we realized it, but I just want to give them a complete